Good evening, everyone. My name is Aditya Sharma, and this is Aircraft Propulsion course being conducted by Department of Mechanical Engineering, IIT Guwahati, under the National Program on Technology Enhanced Learning, that is NPTEL. And this is 10th week of this course, and it's a 12-week course. So for each week's content, we are having one live tutorial session, and this is the 10th such session in this series. The instructor for the course is Professor Vinayak Kulkarni, again from Department of Mechanical Engineering, IIT Guwahati, and I'm a research scholar here at Department of Mechanical Engineering, IIT Guwahati only. So today's topic that we will be discussing is axial flow compressor. So last week we saw centrifugal compressors. So this week we'll be looking at axial flow compressors. So we'll wait for another couple of minutes. After that, we can start with today's session. Thank you. Okay, so we can move ahead with the session. axial flow compressor. So first of all, we'll see the contents of today's session, and then we'll be taking one lecture at a time, its topics and questions. Let's see the contents first. So lecture number, it should have been lecture number 29 to 33. Five lectures total are there in this week's content, week 10's content. So lecture number 29 is axial flow compressor, its velocity diagrams, work done, and then degree of reaction. Okay, this is your lecture number 29. Then there are topics related to it and questions related to it. After that, we have lecture number 30, which is on free vortex condition. Okay, so we'll see what is free vortex condition with respect to axial flow compressors, and what is its importance in the design of a axial flow compressor. Then lecture number 31 to 33 are on numericals. We'll be discussing lecture number 29 and 30. And then we'll see paragraph and its questions based on that, verifications based on that. Right? Yes. So let's move ahead. Lecture number 29, its topics. So we have first rotor and stator, velocity triangles, inlet velocity triangle, then outlet velocity triangle, then compressor work, then work done factor, then degree of reaction. So let's discuss these topics one by one. Lecture number 29. Then rotor and rotor. Now we have seen in centrifugal compressor how the air flow moves in a centrifugal compressor. But then now in axial compressor, as the name suggests, the flow will remain in axial direction, right? So the two directions that are of concern to us is um, axial direction, and then one is your this tangential direction, right? or what the other name which we call it is burn velocity, right? Tangential velocity. So it is something like this. So we have blades. So this is your shaft. This is your shaft. Like this. Then we have blades on it. Let's say this is one blade. One blade will be here. Right? Then you have your casing. Here you have blades this way. Right? Something like this. So this I have shown a single blade here, right? But then this will be, so if this is your shaft, right? If this is your shaft, I have shown one blade like this. So along the circumference of this shaft, you'll have various blades, right? Along this circumference. So I have just shown one blade. And then between these blades, the air will flow in the axial direction, right? So if this is shaft, the flow will move in this direction. So this is your the blades connected to your shaft, right? Those are your rotor blades and the ones that are not rotating, right? So this shaft will rotate, okay? Right? But then there is casing of this compressor, right? Where you'll have blades connected to your this casing, right? And then this will not move. This casing will not move, right? So this shaft will move and the blades connected to it will move, right? So that is rotor, right? Now this will not move, right? The blades connected to your casing will not move. So these are called your stator blades, right? So I hope this is clear. So then again for your stators also along the circumference of the casing, right? So if you have a cylindrical tube, so in its inner walls, you'll have n number of blades. Then there will be flow in this direction. So this is about your what is your rotor and what is your stator in your axial flow compressor. Right? Then you have TS diagram on how the temperature and entropy changes in your rotor and stator. This is your diagram. And here, yes. This is T, this is S. So let me draw the diagram first. After that, So this is your two, three, one. So these are your static lines. This one is your rotor pressure line. Okay. This is for your rotor. This is for your stator. If you see in your rotor, your static temperature is increasing, and then your total temperature is also increasing. T naught one, T naught two is equal to T naught. Okay. So your total temperature is increasing when the flow is moving, or the fluid is moving, or the air is moving through your rotor, and then through your stator when it moves. So your total temperature remains same. Right? Yes. And yes, so this is your TS diagram for your axial flow compressor. Then we'll see the velocity diagrams, velocity triangles. So let's see the velocity triangles. So in velocity triangles also, uh, inlet velocity triangle, and there is outlet velocity triangle. And then there is compressor work based on the velocity triangles. So this is velocity triangles. See. Now I'll just draw the for your rotor the velocity triangle how it looks like. Okay. So then how it looks like, and in your compressor, how do we visualize this? This is showing so this is showing how the fluid is moving in your rotor. Okay. And then this is the velocity triangle. This is your relative velocity. This is your axial velocity. This is your absolute velocity. And this is the blade velocity. Right. So it is again, I would say, very important that we should be able to properly visualize these velocity triangles. So what is happening here? And what are these? These two. So this basically is the top view of your blades. So I have found this here, right? So I was saying that there is one shaft will be there, and along the circumference you'll have n number of blades, right? So out of those n number of blades, two blades we have taken that are there along the circumference, and between these two blades, your flow is moving, and we are analyzing that. Right? And for that, we say that C1 was the absolute velocity, and then V1, and this was moving, right? So this was moving with your blade velocity U1, right? This shaft was moving with the blade velocity U1. So your this shaft, right? So this was moving with your velocity U1, right? So R omega, basically that is U1, right? Then V1 is the relative velocity. So if you take the absolute velocity and the blade velocity, and then considering these two velocities, you'll have one relative velocity of the fluid, that is V1, right? Then alpha 1 is your fluid angle, and beta 1 is your blade angle. So this is the velocity triangle related to your rotor. Okay, this is rotor. Then stator, if you see, sorry. Now, if you see stator, so in your stator, so again, this is the top view of your blades, stator blades. So from the circumference, we have taken two blades, right? And then the velocity triangle related to it is this. right? So this is it. Then few things to note is R. Few things to note are first is your axial velocity. If you see the axial velocity, right? So axial velocity remains constant in your axial flow compressor, right? So your CA1 is equal to CA2, and we can just give it a common name. Right? So this is it. So if we say that this was state one, where the fluid enters the rotor, where it exits the rotor is 2, and then it enters the stator, that is again 2, then it exits at 3. So the absolute velocity at 1 and 3 are approximately equal. Right? So this is for your axial flow compressor. And then we can draw these two diagrams or velocity triangles in one diagram only. So U because remains same. So combined velocity diagram. Let's see. Velocity triangles. Combined velocity triangles of your rotor and stator. Then this whole is your U1 or U2 or U. So I'm writing it U only because it's same for your rotor and for your stator. Then this right side one is for your rotor and the left one is for your stator. Okay. So this is your P1, this is your C2, this is your V2, this is your V1. I hope this is clear. There is no doubt in it. This is your fluid angle. This is your fluid angle or your velocity triangle related to your stator. Or you can call it outlet velocity triangle. Right? The first one you can call inlet velocity triangle. So this basically gives your velocity triangle at your exit. So this one is at your exit of your rotor. This one is at your inlet of your rotor. Okay. So this one is giving of state one and this one is giving of state two. Then this is your blade angle, this is your blade angle 2 at the exit of your rotor. Then this is your tangential velocity for your inlet conditions CW1, and this one is for your second one, right, at the exit. So these is your combined velocity triangles. So these are your combined velocity triangles. Then from these velocity triangles, you get this relation, which is tan alpha 1 plus tan beta 1 is equal to tan alpha 2 plus tan. Sorry. So kindly bear with me. I have cough, dry cough. Okay. So this relation, and this can be written as tan alpha 2 minus tan alpha 1 is equal to tan beta 1 minus tan beta 2. And how we can derive this? So this basically is, so you try to split the blade velocity, u, right? So if you see u, so u is CW1 plus the remaining section. And then if you see from triangle 1, right, from the inlet triangle, so from inlet triangle, it is CA1 tan alpha 1 plus tan beta 1. This is from your inlet triangle, inlet velocity triangle. And you can write this as u by CA1 equals to tan alpha 1 plus tan beta 1. Then again, you can write u as CA2 tan alpha 2 plus tan beta. This is from your outlet velocity triangle. Then again, you can write it as this. This you can do. And then if you equate these two, then if you equate these two, what do you get? You get this. So this is the relation. Then you have compressor work. From here, if you want to find out compressor work, WC. So this is mass flow rate U and CW2 minus CW1. Work velocity or tangential velocity and your axial velocity, these two are being considered in this axial flow compressor. Then from the velocity triangles, if you see, this can be written as EA tan alpha 2 minus tan alpha 1. From velocity triangle, you can see this. And then using this relation, your compressor work can also be written as tan beta 1 minus tan beta. So this is your compressor work. Then there is expression for the temperature. In the stage, there is temperature change from T01 to T02 equals to T03. So for this, the expression has been worked out. So I'll just directly write that down. So the expression is this, right? Then there is expression for the pressure change, right? From P01 to P02 to then P03. So this is the expression for your pressure change, right? A compressor. Then there is one term that is work done factor. So what is work done factor? What is work done factor? So, when we are analyzing our these velocity triangle, right? So this analysis is based on the mean blade height. So when we see the blade here, if you see this diagram, if you see here, so this has some height, right? This blade has some height, let's say h. When we are analyzing and drawing the velocity triangles, so we are taking some mean height, right? Let's say this is the mean height. So at this height, we are analyzing the velocity triangle. But then what happens is that along this whole height of the blade, right? Along this whole height of the blade, the axial velocity CA does not remain same, right? So this axial velocity CA does not remain same along this blade height. So because of this, the temperature change, right, across the whole one stage. If you take one stage, so across this stage, the temperature change that ideally has to be there for the whole compressor. If you take one stage of the compressor, right? So ideally it has to be high, but then because of this profile of axial velocity CA that is not constant along the blade height. So this will be uh, less than that, right? And because of this, we have introduced this work done factor, right? So this basically put this into perspective that delta at stage will be equal to this ideal. So ideally this has to be this, but then because of variations in the velocity at the blade height, it is like this. Then there is degree of reaction. What is that? The degree of reaction is basically the enthalpy change in your rotor, then enthalpy change total in your whole stage. So the rotor is giving enthalpy change to your fluid, and stator is also given. So in the denominator, you'll have the combined effect of your rotor and stator, and in the numerator, you'll have only of rotor. So that is your degree of reaction. So there are formulae for that. So lambda is this, tan alpha 2 plus tan alpha 1. One is this formula. Then if lambda is half, which means if the degree of reaction is half, so half of your enthalpy change is in rotor and half of your enthalpy change is in your stator. In that case, what can we comment about the blade angle and fluid angle? So from velocity triangles, this can be easily, we can deduce this. So what comes out from here is, so I'll just directly write this down, this. So this has been worked out in the lecture. So I'll just place the link in the description and from there you can see. So this is it. So your if your degree of reaction is half, that case, your fluid angle from inlet will be equal to your blade angle from the outlet. And then your fluid blade angle at the inlet will be equal to your fluid angle at the exit. Right. So this is the degree of reaction for your related to your axial flow compressors. Then the topics of lecture number 29 are over in that case, and we'll move on to questions. The first question is this. So please have a look at the question and try to see what can be the right answer to this question. So this question says that which of the following is true for the flow through stator blades of an axial flow compressor? So from the stator blades, your fluid is moving or your air is moving. So which of the following is true? Your stagnation temperature remains constant. Your stagnation temperature increases, it decreases. Your static pressure decreases. So your static pressure increases. Right? The whole purpose of having different components in compressor is to increase the pressure. You want to increase the pressure of the air or fluid. Right? So this cannot be D cannot be true. But then what happens to your stagnation temperature? So then what happens to your stagnation temperature? We have seen this. If you see the TS diagram, so your stagnation temperature remains constant. Okay. From the TS diagram, you can comment on this question. The total pressure increases, but then your total temperature remains constant. So in that case, A. Question number one, A option is the correct. Then moving on to the next question. I hope this is clear. So in an axial flow compressor with increase in axial flow velocity, the compressor work. What happens with the increase in axial flow velocity? So this is direct formula. If you see, this is your compressor work. Here, this you see axial velocity. If you increase, what will happen? Your compressor will increase. So this increases. E is the right answer to this question. This was question number 2. I hope this is clear and there is no doubt in it. If you have some doubt, you can just type in the comment box and I'll be happy to answer. Then moving on to next question, question number 3. For an axial flow compressor, the area of rotor blade at the outlet is. So what will be the right answer to this question? So in your axial flow compressor, your rotor blades act as diffusers. Okay, diffusers means your inlet area will be less and your outlet area will be greater. Area of the at the outlet is larger than that at the inlet. Okay. Like this. So if you take one stage, this is your inlet, this is your diffuser action. So this was question number 3. Then we have next question. It says that in an axial flow compressor, the absolute velocity of air passing through the rotor, what happens to the axial flow, the absolute velocity in the axial flow compressor? The 4 options we have with us. First is it increases, second is it decreases, third is it remains constant. Fourth is we cannot comment on that. All the data is sufficient. We cannot directly comment on it. So what will be the right answer to this question? What happens to your absolute velocity? We can comment on it if we see the combined velocity triangle diagram. So now if you see the velocity triangle, you see C1 and you see C2. You will realize that C2, if you see the length of C2, it is greater than C1, which essentially means that your absolute velocity for exit of rotor is greater than your absolute velocity for your inlet of rotor. That is C2 is greater than C1. Is that correct? Right. So absolute velocity, if you are passing through the rotor, what happens to this absolute velocity? It increases from the combined velocity triangle diagram. You can tell that here is the correct option to this question, correct answer to this question. Then moving on to next question. So please have a look at the question. So maybe we can take a 5 minutes break. After that, we can discuss this question because already it's 7 o'clock. So let's take a small 5 minutes break. After that, we can continue the session. So let's continue with the session. And we have question number 5 with us. This is that for an axial flow compressor, which of the following velocities remains constant from rotor's inlet to its outlet, whether it's relative velocity, whether it's absolute velocity, whether it's blade velocity, whether it's whirling velocity. The relative velocity is V from inlet to outlet, V1, V2, absolute velocity C1 to C2. Blade velocity U1, U2. This is CW1, CW2. So, which of the four is correct one? Again, going back to the velocity triangle diagram. If you see, U remains constant. Even the axial velocity we consider as constant. So, that case, U1 is equal to U equals to U. C is the correct option to this question. So, ask question number 5. Then moving on to next. So we don't have next question for this lecture number 29, but we have next lecture, that is lecture number 30. So lecture number 29, its topics and its questions are over that I have with us. With me, sorry. Then lecture number 30 is there. If free vortex condition has been discussed. See what is free vortex condition. Then is there. Then these three lectures are there. When numericals have been discussed. These lectures, I'll give the link so you can directly see the numericals there only because all the topics are there in lecture number 29 and 30 that are to be discussed. Numericals, I believe you can watch through videos only. Here, we'll solve few numericals based on the that we can. Then what is free vortex condition? So this is lecture number 30. This is free vortex condition. This free vortex condition. Basically, we assume that there is radial equilibrium. Now, what is radial equilibrium in the compressors? So then I will move to this diagram, this rotor and stator diagram. So I have already mentioned this, that when we are seeing the velocity triangles and when we are analyzing the fluid velocities that we encounter in axial flow compressors. So we are basically seeing the mean height of the plate at which we are analyzing this fluid flow, right? But then you have this whole height of this plate, and you don't want, so if this is your plate, right? So this is some plane one, this is second plane. Let's say this is one plane, this is two plane. You don't want that velocity should be there in the radial direction, right? Hope you understand this. You don't want this to be towards the this axis of the shaft. You don't want it to be in the radial direction. You don't want your fluid to be radial direction. For that, you say that uh, you want radial equilibrium. The radial equilibrium means the flow will remain in this two directions. One is axial and one is tangential, but not in radial direction. Right? And when you give this statement that fluid has to be in radial direction, and then you analyze your fluid, so there comes out this statement, which is this R into C omega equals to constant. So if you want radial equilibrium in your exit flow compressor, so this has to be for R into C omega has to be constant. It essentially means that as your radius from the axle of the shaft, if you see, you take the radius. So as the radius increases, so radius increases means we are moving from your root to tip. Okay. So this is your root. This is your root of the blade, and this is your tip of the blade. The one connected to your hub of shaft is your root. So as you increase the radius, which means you're moving from your root towards tip. Okay. So as you move from your root towards your tip, your R will increase. In that case, you'll have to reduce the tangential velocity. So when you will keep reducing the dimension velocity, then only your flow in the this for this whole blade between the radial equilibrium. This essentially is the meaning of this free vortex condition. Then is your degree of reaction. If you have to relate it with R, so if you increase your R, so if R increases, so your second term will decrease and your degree of reaction increases. Degree of reaction increases means the, the stagnation, this the enthalpy change in your rotor will be keep on increasing as you uh, move towards tip. Uh, enthalpy change in your rotor with respect to your whole stage keeps on increasing. So your relation with R of the integrated function. Okay. Then we'll see questions then. So question number 6. For the free vortex condition of an axial flow compressor, as the radius along the rotor blade height from the root increases, as the radius increases, basically, the degree of reaction, just discuss this. If R increases, your lambda increases. Because your second term, this term will decrease. So R is in denominator, so this term will decrease. So A is the correct answer to this question. Then we'll move on to questions, numerical questions. So first, please have a look at the paragraph. Then we'll start to take questions based on this paragraph. I hope you have read this paragraph. It says that air enters at 300 Kelvin. So it's a 9-stage axial flow compressor. And sorry, mass flow rate is this. The pressure ratio RP is this. Isentropic efficiency is this. Eta C, right? The compression process is adiabatic. The compressor has symmetrical blades. Okay. Then the axial velocity of 140 meter per second is uniform across the space. So this is CA, and the mean blade speed of each stage is 180 meter per second. So mean blade speed is speed blade speed. This is specific heat at constant pressure, and this specific heat ratio 1.4. Then we'll just write down what is given to us and then start solving the questions. First is the actual temperature at the exit of the rotor blade in Kelvin is temperature at the exit. This is let's find out. So question number 7 to 11. What is given is number of blades, number of stages. So if you understand stages, the pair of rotor and stator, right? 9 stages are there. And isentropic or NC also, we have denoted it by NC also. So this is 88%, that is 0.88. Then mass flow rate is also given 6.4 meter per second. Have one is meter Kelvin. RP is 5.0. PA is 140. Then U is 180. PP is 1.005 per kg Kelvin. And gamma is 1.4. So this is all that is given to us. Then we'll see the temperature at the exit. Question number 7, solution. So for isentropic case, what is there? T2 dash by T1 is equal to T2 by T1, gamma minus 1 by gamma. From here, what will we find out? We'll find out T2 dash. Why so? Because that we will be using the formula for efficiency of isentropic efficiency of compressor. This is T1 into T2 by T1, gamma minus 1 by gamma. So this is 300 into 5, 0.4 by 1.4. Now, if you calculate this, this will come out to be 475.14 Kelvin. This will come out like this. Then, then we know that this is asymptotically efficiency will be less, and in reality, this is high. From here, you can calculate P2. It's P1 plus P dash minus P1 by 300 plus if you work this out, it will come out to be this. It's 490. The next question is, then next question is, Power input to the compressor in kilowatts is power input to the compressor in kilowatts is this is mass flow rate into Cp into delta T. Mass flow rate is 6.4, Cp is 1.005. This will come in then kilowatt only, because this is kilojoule per kg Kelvin. T2 minus T1, 6.4 into 1.005 into 499.02 minus 300. If you calculate this, this will come as this. This is the power related to this compressor that will be give to this compressor. Okay. They pressurize the gas so that its pressure ratio is 5. Then section number 9. Stage total temperature rise. Stage total temperature rise. So if you see, there are 9 stages. Right? So it is something like this: 1, then 2, then this way. This is 9. This is 1. This is 2. This is 9. 9 stages are there. And here it is T1. This is T2. So we will suppose that in each stage the temperature rise is same, right? So we know what is T2 minus T1. So for single stage, we can calculate this by N. So this is 499.02 minus 300 divided by N. N is 9. So if you calculate this will come out with 22.11. Then next question is inlet rotor blade angle in degrees is, and the question next to it is the outlet rotor blade angle. So we need to calculate first beta 1, then we need to calculate beta 2. So let's solve this. Question number 10 solution. So we'll have two equations in beta 1 and beta 2. Then we will cancel out either beta 1 or beta 2. From there, we will calculate either beta 1 first or beta 2 first. And from that, there we can get the second beta. So we will start from here. Work done per kg per m dot. And you can write this way. For this, if we don't want to consider the mass flow rate, in that case, we can write it this way. Then from here, you will get delta CW. Okay. So this is UCW2 minus CW1. This is basically work done on the compressor. And CP delta T is again work done from the temperature change. Now for stages, for symmetric stages, so delta C is A tan beta 1 minus tan beta 2. So from velocity triangles, this is very easy to reduce. The first is this, first is this, second one is this. Okay. Then there is this degree of reaction, A by 2U, tan beta 1 plus tan beta 2. This is there. Implies 2U lambda by CK is equal to tan beta 1 plus tan beta 2. This is third. So we will now consider equation number 2 and place delta CW in 2. From 1 and 2, what we can say, we can say that CP delta TS divided by U into CA is equal to tan beta 1 minus tan beta 2. Now tan beta 1 and beta 2 we do not know, right? But we can place the values for 5 into 1000. Okay. 1000 is for kilojoules, so we want it in joules, SI units. Then this is delta T for each stage is 22.1. U is 180. Axial is 140 is equal to tan beta, sorry, tan beta 1 minus tan beta 2. So if we solve this, this will come out to be 0.88 is equal to tan beta 1 minus tan beta 2. Now, this is it. Then from third equation, we have 2 into 180 into, because blades are symmetrical, in that case, your degree of reaction will be half. Okay. So this is tan beta 1 plus tan beta 2. Implies 1.28 is equal to tan beta 1 plus tan beta 2. So this is fifth. So now we have fourth equation and fifth equation. From here we can eliminate tan beta 2. So from 4 plus 5, what we have is 2.16 is equal to 2 tan beta 1, implies tan beta 1 is equal to 1.08, implies beta 1 is equal to 47.20. This is there. Then question number 11 is asking for outlet rotor blade angle in degrees. So using sticks, in 4, this 0.88 is equal to 1.08 minus tan beta 2, implies tan beta 2 is equal to 1.08 minus 0.88. implies theta 2 is equal to 11.3. So this is the blade angle for theta for exit of rotor, and this is for inverter. So this is it about today's session. Then we have come to the end of this session. In that case, I can conclude today's session. So there were total 5 lectures. Lecture number 29 to lecture number 33. Out of these 5 lectures, first 2 lectures had topics, then remaining 3 lectures had numericals. So we discussed first 2 lectures. Lecture number 29, where everything related to axial flow compressor, its velocity diagram, its PS diagram, the expression for compressor work, the temperature change across the compressor, the pressure ratio across the compressor. These things were discussed. Then we saw questions, 5 questions based on lecture number 29. Then we moved on to lecture number 30, which was on the free vortex condition, which is related to the radial equilibrium that we want in our axial flow compressor. So this we need to consider while we are designing the compressor. Okay. From the radial equilibrium condition, we get the free vortex condition, which basically is R into CW equals to constant, which means that as you move from root to tip of the blade, of the rotor blade in your axial flow compressor or axial compressor, in that case, your tangential velocity should decrease. And its relation to degree of reaction has been shown, which says that as the this R, the radius increases, as we move towards tip, the degree of reaction increases. So this was lecture number 30. Then saw one question on that. And after that, we moved on to numericals. So this numerical was on axial flow compressor, where symmetric blades were there. And then we found out exit temperature, then power related to compressor. Then saw blade angles. And then for each stage, how much temperature rise is taking place. So this all was discussed in this today's session. So this is it for today. Next session again will be on coming Tuesday from 6 to 8 p.m. Thanks for watching this session. Goodbye.